In today's lesson, we're going to talk about solving linear systems. And a linear system is simply more than one, usually two, linear equations, or equations of lines. We're going to talk about three different methods that can be used to solve these systems. And so before we do that, let's talk about what does it actually mean to find the solution of a system. So in example 1, I want to know, is the point -2, 1 a solution? For a point to be a solution, it has to satisfy or work in both equations. In other words, it has to lie on the graph of both of these lines. So is -2, 1 a solution to the system? Well, I can take -2 and plug that in for x, and then I'll take 1 and plug that in for y. And so in the first equation, the top equation, I end up getting -2 minus 3 is -5, and that definitely does work. However, if I take -2 and plug that in for x, and I plug 1 in for y into the second equation, I'm left with -4 plus 1, and that is definitely not equal to 4. And so because this point only lies on one line, it doesn't lie on both lines, or it doesn't work in both equations, we would answer this question with no, this point is not a solution. So how do we find solutions of these linear systems? Well, again, we're going to talk about three different methods, and we'll start by talking about the method of graphing. If I want to figure out what point satisfies or lies on the graph of both of these lines, I can graph both of them on the same set of axes, and then just see where do they cross. And so to graph this first line, I am going to solve it for y, so I minus the 3x. This line is now in that slope-intercept form. We kind of reviewed that quickly last time. It's in that y equals mx plus b form. So the m is -3, or -3 over 1, and the b is +4. So I can use this information to create a graph. I can also make a table of values, just like we did last time. But let me show you how it works to use the slope to create a graph. So if the y-intercept is 4, I'm just going to go up and put a point at y equals 4. And then if slope is -3 over 1, that's rise over run. So that means I can go down 3, that's the -3, and to the right 1. And there's another point on that line. And we could repeat this, down 3 over 1, as many times as we need, and then we can just connect the dots with a nice straight line. So there's the graph of that first line. If I want to use the same method on the second line, let's see, we've got 2x minus 4y is -2. I'm going to solve for y, so I'm going to start by minusing the 2x, and then I'm going to divide everything by -4, all of the terms. So now I've got y equals, well, 2 over 4 is a half. And a negative over a negative does become a positive. So I end up with y equals 1/2 x plus 1/2. So both my slope and my y-intercept is 1/2. So to graph this, I'm going to start at 1/2. So I'm going to put a point right there at 1/2. And let's see, slope is rise over run, so that means I have to go up 1. So I'm just going to have to estimate where that is. That's going to be at about 1.5. And then let's see, we said up 1 and then over 2. So there's my second point. And we could do that again, up 1, over 2, third point. And if I connect the dots, there's the line of that second equation. So if I'm trying to figure out what point satisfies both or lies on the graph of both of these lines, I just have to see, well, where do they intersect? Where do they cross? And I can visually kind of estimate where they cross. It looks like they cross at x equal 1 and y equals 1. And so that's my solution. I could write that as the ordered pair 1, 1. And that's it. That's the answer to this problem. If we wanted to check our work, we could. We don't have to, but one way we could check is we could take those numbers and plug them into the original equations. and see if we get true statements. If you plug 1, 1 into the first equation, yep, 3 plus 1 is 4. And if you plug 1, 1 into the second equation, let's see, we get 2 minus 4. Yeah, that works as well. That's negative 2. Again, you don't have to check your answers. Just a nice thing to do if you're working on, for example, a test and you have a little bit of extra time. Now notice in the previous example, the lines crossed at only one place. This is what's going to happen really most frequently. And I'm calling this case 1. In fact, anytime your two lines have different slopes, and so that's what I have drawn in case 1. So anytime the slopes are different, the lines are slanted in a different direction, you're always going to have one solution. There's going to be only one point where those two lines cross. The second thing that could happen is you could end up with parallel lines, and that's what I have shown in that second graph. Parallel lines are never going to cross, and in that case you would have no solution. Two lines are parallel if they have the same slope. They're slanted in the same direction, but notice they have different y-intercepts. Finally, the last thing that can happen, case 3, is the two lines you're given could actually be the exact same line. And in this case, we have an infinite number of solutions. Every single point on the line is actually a solution. In this third case, when you have the same line, so same slope, same y-intercept, every single point on that line is actually a solution. So we have an infinite number of solutions. So 3 cases, 1 solution, no solution, infinite number of solutions. Finally, there's a little bit of vocabulary that you might see in your textbook. I'm not going to test you on this on an exam, so you don't need to write this down, but it'll help you read your book. This case 1 with one solution, we say that's an independent and consistent system. No solution, we say it's inconsistent. And finally, it's a dependent system when there's an infinite number of solutions. I really just want you to know the 3 cases: one solution, no solution, infinite solutions. So can we determine which case we have without actually creating a graph? We can if we compare the slopes and the y-intercepts. To find the slope of the first line, I'm going to put it in slope-intercept form, so I'm going to solve it for y. I have to subtract the 2x, so 3y is minus 2x plus 6, and then I'll divide everything by 3, and that gives me y equals negative 2/3 x plus 2. So this first line has a slope of negative 2/3, and it has a y-intercept of 2. Now, the second line is already in slope-intercept form. This second line here, we can see that the slope is the number in front of the x. It has a slope of negative 2/3 and a y-intercept of 1. So we've got same slope, negative 2/3 for both, but the lines are actually different. We have different y-intercepts, and so that tells me this is that second case. These are parallel lines. And so to answer the question, how many solutions? There is no solution, or you could say none. These lines never cross. So one way that we can find the solution to a linear system is by graphing. We're trying to find a point that lies on both lines, or numbers that satisfy both equations. Now, graphing is a great method because it's very visual, but as you can imagine, sometimes it's hard to get a really accurate answer. It's hard to read exactly where that point of intersection is. So we're going to take a look at 2 other methods that perhaps are a little bit more precise. And the first one is the method of substitution. To use the method of substitution, we're going to start by solving one equation for one variable, for one letter. And then we take that result and plug it into the other equation. Now, it doesn't matter which equation you solve for which variable, but if there is a variable that doesn't have a number in front of it, like right here, this y in the first equation, that's going to be the variable that's easiest to solve for. And the reason is, if I was to try to solve for, say, x, At some point, I would be dividing by 3, and that's going to work. I can do that, but it'll introduce fractions into the problem and make the problem a little bit harder. So again, if there's a variable that doesn't have a number in front of it, that's what you want to solve for. So I'm going to take the first equation. To solve it for y, I have to minus the 3x. So y would equal minus 3x plus 3. And then I'm going to take that result, and I'll plug it into y for the second equation. So now we've got 2, but instead of y, I'm going to put in this minus 3x plus 3. And then there's another minus 3x equals 3. So again, what I did is I took the first equation, I solved it for y, and then I plugged that in for y into the second equation. And so the advantage is now I have an equation with one variable only, and so this is something we can solve. We can get rid of parentheses, so negative 6x plus 6 minus 3x is 3. Combine like terms. Negative 9x plus 6 is 3. Get the x by itself. So negative 9x is negative 3. Divide by negative 9. And it looks like we've got a fraction, x equal 1/3. 3/9 reduces to 1/3. Now, we're actually not done with the problem. We're trying to find an intersection point. Where do the two lines cross? And so we're going to have to take our solution, and we can plug it into any one of these equations to try to find the y value. I'm going to plug it into this equation right here. Oops. So I'm going to replace that x with 1/3, and now I've got y equals negative 3 times 1/3. That's going to be a negative 1. 3 divided by 3 is 1. Plus 3, or y equals 2. And I could also write my answer as an ordered pair. These lines intercross at 1/3, 2. These lines intersect, at x equal 1/3, y equals 2. And so again, this is the method of substitution. It's a great method because it gives us this precise answer, which would have been really hard to get from a graph. In front of it, for example, in this example 6, if I were to say solve for x in the first equation, I'd have to divide everything by 3. That would give me fractions. And the same would be true if I were to solve for y, I'd have to divide by 4. And so I'm going to show you another method called the method of elimination. This is also a method that's really helpful when you get to other types of systems in Math 121. And so in this method, the concept is we are going to add multiples of the equation together so that one of the variables actually cancels out or is eliminated. So in this case, if I want to eliminate the y's, their coefficients, the numbers in front of them, have to be equal but opposite. And so if I take the second equation and multiply it by 2, notice that gives me 4x plus 4y equals 6. Now the numbers in front of the y's are the same, but opposite signs. And so that means if I add these two equations together, the y's are going to disappear, and I'm left with 7x equals 11. And this is an equation that's pretty easy to solve. You just have to divide by 7. I could take this number, I could plug it into either one of my equations to figure out what the y is, or I could actually use that elimination method a second time. So if I want the x's to cancel out, again, those coefficients have to be equal but opposite. I could take my first equation and multiply it by 2. And I can multiply the second equation by negative 3. Let's see, first equation by 2, that's going to give me 6x minus 8y equals 10. Second equation by negative 3, that's a negative 6x. And that's what I want. The x's have numbers that are equal but opposite. And then 3 times negative 3 is negative 9. So now we can add these two equations together. This time the x's disappear, and now I have negative 14y equals 1, so y would be negative 1 over 14. And there's my solution. My x value is 11/7, and my y value is negative 1 over 14. So again, the process is you have to multiply things by the equations. You have to basically transform the equations so that one variable has equal but opposite coefficients. So again, I multiplied the second equation by 2 so that I would have a minus 4y and a plus 4y. Then when I added the equations together, that variable canceled out, and I could solve for x. If I multiplied the first equation by 2 and the second one by negative 3, that gave me the 6 and negative 6. X's cancel out, and I could solve for y. Finally, if we have a system that has fractions in it, we can actually get rid of those fractions before we do anything else by multiplying everything by the least common denominator. This is very similar to what I did in that first lesson when I was solving an equation. And so in this first equation, let's see, we've got denominators of 3 and 5. And so my LCD would be 15. So I'm going to multiply everything by 15. In the second equation, I have denominators of 6 and 5. And so I can multiply everything by 30. 30 is divisible by both 6 and 5. So first equation, we multiply by 15. That gives me 15x over 3 plus 15y over 5 equals 7 times 15, which is 105. 15 divided by 3 is 5. 15 divided by 5 is 3. So I'm left with the equation 5x plus 3y equals 105. I do something similar for the second equation. I'm going to multiply everything by 30. So 30x over 6 minus 60y over 5 equals negative 120. That becomes a 5x minus 12y equals negative 120. And so now I can use either substitution or elimination. I would probably use elimination just because I noticed that both equations have a 5x in them. And so all I have to do is take one equation, perhaps the second one, and multiply it by negative 1, and then I'll have equal but opposite coefficients. So second equation times negative 1 is negative 5x plus 12y equals 120. And then if I add that to my first equation, 5x plus 3y is 105. The x's go away. I get 15y equals 225. So that means y would equal 225 divided by 15. And 225 divided by 15 is 15. We can take that number, we can plug it into either equation. I took the y equals 15 and just plugged it into that first equation. So 5x plus 3 times 15 equals 105. I have my work written out. I ended up getting x equal 12. So my solution would be x is 12, y is 15. Finally, I want to show you what happens in those special cases if you have parallel lines, that case with no solution. Your problem might look something like what I have written down in red. Notice that if you try to use the elimination method, both the x's and y's eliminate, and you're left with 0 equals 9. This is a false statement, and so this is what tells me there is no solution. So anytime the x's and y's disappear, and you end up with a false statement, that means there's no solution. Our other special case was when we had infinite solutions, when we have the same line. And if you try to solve a system with infinite solutions, again, the x's and y's are going to disappear, but you'll end up with a true statement, like 0 equals 0. And that's what tells you you have infinite solutions. So if all your variables disappear, then it means you just have one of those special cases. False statement would be no solution. True statement is an infinite number of solutions. That's it for this lesson. I know there's a lot of material in here. Please let me know if you have any questions or if any of the homework problems are confusing.